My name is Hauran. I'm from the University of Michigan, Department of Electrical Engineering and Computer Science. This summer, I have been working with Professor Zhongyang Zhang on the project High Performance Channel Codes for Power-Efficient Wireless Communication. The objective of my research is, first, to learn some basic knowledge about high-performance channel codes and their way of decoding. Second, to build an architecture-level decoder for a specific high-performance channel code. Then, I will construct and configure a library that contains the blocks of decoding that could be applied to other codes. At last, I can use a library to guide the performance of different codes under different standards. The code I implemented is the low-density parity check code. At first, I can give you some background information on it. The adoption of this capacity-approaching LDPC codes is one of the keys to achieving a lower transmission power for a more reliable communication. On the slide is a representation of an LDPC code in parity check matrix and vector graph. The decoder I implemented is using the approximate sum product algorithm. This is the process of decoding. The variable nodes send messages to the check nodes along the edges defined by the vector graph. And then the log likelihood ratios are recomputed based on the parity check constraints at each check node. In this case, it's the minimum approximation, and then return to the neighboring variable nodes. Each variable node then updates its decision based on the channel output and the extrinsic information received from all the neighboring check nodes. This is the canonical architecture that I have been using in constructing the decoder. In this architecture, column partition is applied to divide the decoder into several parallel units, where each unit processes certain bits. This figure illustrates the architecture of the mean-sum product decoder. Memory M0 stores the variable to check messages, and memory M1 stores the check to variable messages. The check node here is used to compute the minimum of the variable to check messages. The sum is marginalized locally and then stored in M1. This architecture minimizes the number of global interconnects by performing marginalization within the local processing unit. After a general view of the decoding algorithm and architecture, I constructed the library that contains the processing blocks for building the decoder, the controller, the address generator, the processing unit, the check node, the noise generator, and the decision block. Then I configured the whole library. The next step, I wrote a MATLAB script to construct the design using the blocks in the library. After I finished the script, a click on the Simulate button. The whole part of the design will be automatically constructed. After a long debugging process to make sure the design functions well, I added several software register masks and the platform configuration. Finally, I can run BPS to compile it. The most interesting part of this project is that we have internet-accessible FPGA boards for us to test the bit file. We don't need to program it on the FPGA board by hand. Then we can use Impact to program the bit file on FPGA and then type commands on hyperterminal to see the outputs. Giving values to the register, we can get the outputs on the different standards. Based on the outputs from the test, we can make a table for the bit error rates and frame error rates under different signal-to-noise ratios. Then I plotted the graph of BER and FER versus SNR to see the performance of the decoder. The performance looks quite good, so I succeeded in making a decoder for the given codes. This time, using a library I configured, I can easily appear to different codes only by changing several parameters in the controller and the initialization files. Then I tried different codes for different rates. Rate 1/2, rate 5/8, rate 3/4, and rate 13/16, and finally get their performance. In this way, we can easily compare their performance for codes of different rates, iteration numbers, quantization, and so on. Until now I have completed all the goals of my summer research. In the future, I might have to construct a library for more efficient layered architecture to improve throughput and perhaps work on a more efficient layered decoding algorithm to improve the efficiency of decoding. Above is the representation of my summer research. Next is the reference page. Thank you very much for your attention. Thank you.